Hi, hello everyone. This is Dr. Chiranjeevi Manike, Professor and Head of Data Science and Cybersecurity Department, MLR Institute of Technology, Hyderabad. As part of data mining video lecture series, in this lecture we are going to discuss about Naive-based classification. Previous lecture I had given a brief idea about the Bayes theorem, and I gave a simple real-time example also. So in this lecture we are going to discuss mainly how this Naive-Bayes classifier works. So it could be divided into the four or five steps. So let us try to understand. So what is the importance of each term in this Bayes theorem, how the probabilities would be calculated, etc. So that in the next lecture we will solve a problem, that is a running example problem, by applying this Naive-Bayes classifier. So let us start with how. So here our objective is to understand how the Naive-Bayes classifiers works. As I said, the entire process would be divided into, like, let us say, the 5 steps. So the first we have to understand and how the data would look like. So the data, as I just in previous lecture also I explained what the data set would contain, mainly the basic concepts. So here let D is a training set of let D is a training set of tuples. D is a training set of tuples with the associated class labels. Training set with the associated class labels. So this is, let us take data set. So this is a data set with the associated class labels. It has class labels. Let us say the last column represents the class label. This is a class label. Class label. And it has the attributes, like n number of attributes, a1, a2, and so on, n number of attributes. So any data set would contain the n number of tuples. So let us say each tuple in this data set D would be represented in the form of a vector, an n-dimensional vector. So that would be, like, suppose if you take X is a tuple in this D, and it would be represented as an n-dimensional vector of attributes. Like, for example, x1, x2, and so on, xn. So X would be represented as n-dimensional vector, like x1, x2, and so on, xn. And these are the measurements. So n measurements on these attributes a1 to an for the tuple x. These x1, x2, x3, and so on, xn depict the measurements taken on the attributes a1, a2, a3, and so on, an for the tuple x. Next, this is the basic information. So we must know what are the attributes, and these are the values. This would be represented as, like, suppose x, if you take like xk is a value or a measurement value for a attribute, a tuple x, for tuple x, value of a attribute a for tuple x. So this is the basic information required to understand what are the next steps, what are the different terms in this Naive-Bayes classifier. And second one, suppose the D has m number of classes. D has m classes. Like if the D has m classes, then that would be represented as, suppose C1, C2, and so on, Cm. There are m classes. So given a tuple x, that is belongs to the data set D, here the classifier would predict the class label of x. It would predict the class label of x. So that means, like suppose Ci is a class label of a tuple x, then this is the highest posterior probability. That means the Bayes theorem predicts the probability, that is predicts the class label of tuple x. That means if Ci is the class label of a tuple x, if and only if the probability of Ci given x is greater than the probability of Cj given x for all the j value in between 1 and m, and j not equal to I. J is not equal to I. So that means if a classifier predicts the probability of class label, that is the Bayes theorem predicts the probability of the class label of a tuple x, that is, let us say the Ci is the probability, Ci is the class label, that would be predicted using a Bayes theorem. Then that probability, that is probability of Ci conditioned on x, should be greater than the probability of Cj conditioned on x, where I, here the j value varies in between, that is in between the 1 and m, because there are m number of classes. These are the m number of classes it has. So, and this is called as, that means for a class Ci, the probability of Ci given x is maximum. For a class Ci, the probability of Ci given x is maximum, and that is called as a maximum posterior probability. Maximum posterior probability, right? So that means if you take the probability, that is Ci given x, that equal to, as per the Bayes theorem, the probability of x given Ci times probability of Ci over probability of x. So here we have to max, this is constant for all class labels. This is constant for all class labels. So our objective is, because as per the Bayes theorem, the probability, like the class label, that is Ci with the highest probability that is belongs to, or the class label of a particular tuple x is Ci, that means that should be the highest probability, that is called as a maximum posterior probability. This is a posterior probability. these two terms, as we already discussed in the previous lecture, this maximum posterior probability. So to maximize this posterior probability, and here this is constant for all the class labels in this case. So only to maximize this, the posterior probability, that is probability of Ci given x, so we have to maximize the numerator, that is probability of x given Ci times probability of Ci. So that is probability of x given Ci times probability of Ci. So here the probability of Ci is a prior probability. Probability of Ci is a prior probability. So for example, if we don't know the probabilities of this class labels, so then most of the case we assume that all the classes are equally likely, all the class labels. If so, then the probability of the prior probability is C1 equal to probability of C2 equal to probability of C3 equal to, and so on, equal to probability of Cm, because there are m number of classes. So, and this is the situation, then we have to maximize the probability of x given Ci, probability of x given Ci. So how we can maximize this? That means for each attribute, for each value of an attribute, like suppose x is a tuple and the attributes are, let us say, a1, a2 and so on, an. So for each attribute we have to calculate this posterior probability. So the calculating the posterior probability for each attribute is very difficult. It is a highly complex process. It's a costly process. So to avoid this, so they made an assumption that is called as a class. They made an assumption that is called as a class conditional independence. Conditional independence. So that means, what does it means? So our objective is to maximize this posterior probability. So but if you want to calculate the posterior probability for each attribute in the data set or for each tuple, then that would become a costly process. So they made an assumption, that is assumption made by the Bayes in Bayes theorem, that is the class conditional independence. That means there is no dependency among the attributes. There is no dependency among the attributes. So that can be defined as the probability of x given Ci equal to, so product k varies from 1 to n, p of xk p of xk given Ci. So if you expand this, because the tuple x is a n-dimensional vector like x1, x2, x3 and so on, xn. So then this would be written as the probability of x1 given Ci times probability of x2 given Ci times probability of x3 given Ci times and so on, times probability of xn given Ci. Because the attributes are independent, there is no dependency among the attributes. So here the calculation of this conditional, posterior probability, conditional probabilities from the tuples in the data set D is very easy. So here let me take one simple example. Okay, let us take this one. For example, if you take xk is a value, it is a value of attribute A for tuple x. X is a value of attribute A k. Let us say k for tuple x. So then, while calculating this the conditional probabilities, that is mainly the posted probabilities, we'll check each and every value of the attribute. Suppose here there would be two choices, like suppose the first one, let us say ak, the attribute, the particular attribute is a discrete value, and the second, if suppose ak is a continuous attribute. If ak is a discrete attribute, so then we'll directly calculate the probabilities, like we'll divide the value, that is for example ci and the database D, like suppose for a particular class the total number of tuples, and then the total number of tuples belongs to the class ci, and the value under this tuple, the value which is xk. So we have to count that value. So that comes here. So that would be the probability, the conditional probability we calculate. If it is a discrete value, attribute ak is a discrete. If it is a continuous, so then continuous means, so that continuous data would follow the Gaussian distribution. So Gaussian distribution with the mean mu and the standard deviation sigma. So then it could be defined as g of x mu sigma, that equal to 1 by square root of 2 phi sigma e to the power of minus x minus mu whole square by 2 sigma square. So that the probability of xk given ci equal to g of xk sigma ci and mu ci and sigma ci. That means for each xk, for each value, we have to calculate the mean, that is average, and also the standard deviations. So next, that is we have to calculate the last, like suppose the classifier predicts the class label. The classifier predicts the class label of tuple x. Classifier predicts the class label of tuple x. That means the probability of x given ci times probability of ci. Probability of x given ci times probability of ci would be greater than, or I'll write here, the probability of x given ci times probability of ci is greater than the probability of x given cj times probability of cj. So for all, that is j value in between 1 and m. M is the number of class labels. and j should not be equal to I. Okay, so and this is the maximum value. This is the way we can maximize the probability. Like suppose there are like 5 classes, let us say 1 2 3 4 5, and there is one tuple called as a x. So then what is the probability of like the class label of x 1, and what is the probability that the class label of a tuple x is 2, like that. So we will calculate, and among this, which is the maximum posterior probability, maximum posterior probability. So that would be predicted by the naive Bayes classifier. So that is a major object. So it has to predict the class label with the maximum probability. So that's why we have to always maximize this, the posterior probability Ci, probability of Ci given x. So this we could not, because it is a constant. So this could be maximized. So again, suppose if we don't know the class labels of this, the Ci, so in that case all the class labels are equally likely. So then the probability, like the P of C1, probability of C1, prior probability C1 equal to probability of C2, and so on, probability of M. So in that case, this term, like this posterior probability, that is probability of x given Ci, plays the major role to maximize this posterior probability. So that's it. We discussed about the naive Bayes, how the naive Bayes classifier works. So let us quickly summarize what we have discussed here. So we have to understand what is a data set, that is a set of training set of tuples with associated class labels, and a tuple x would be represented as a n-dimensional attribute vector, that is x1, x2, and so on, xk. Those are the measurements of attribute A for the tuple x. So then mainly the Bayesian classifier or the classifier would predict the probability of a class label. Like suppose if x is a tuple, then our classifier would predict the class label of that particular tuple. So here any class label, let us say like Ci, with the maximum posterior probability, that is probability of Ci given x is maximized, then that is called as a maximum posterior probability. And the class conditional independence, that means because for each attribute we have to calculate this value, so it would be computationally more expensive. So they assume this called as a class conditional independence. That means there is no dependency among the attributes. If so, then the probabilities of conditional probabilities would be calculated as a product of this. We would express like this. So then the value which we are going to take, that is an attribute value, if it is a discrete value, then we calculate the frequencies, then we calculate the probabilities. And if it is a continuous, so the continuous data would follow the Gaussian distribution with a mean mu and a standard deviation sigma. So from that we can derive it. So in this case we have to calculate this sigma, that is a mean and the standard deviation for the each value. So the classifier need to, if a classifier or the class label of x, the class label of x is Ci, then the probability of x given Ci times probability of Ci should be greater than the probability of x given Ci times the probability of Cj for all j value that is in between the 1 and m, where j is not equal to I. So thank you for watching. Next video I'm going to explain the example, numerical example, how we are going to calculate all these probabilities by applying this naive Bayes classifier. Thank you.